Well, hello everyone. Now, last video we explored the IGBT module and we took a look at how the capacitor and the gate resistor change the turn-off voltage spike in it. But, I said in last video, this one's going to be all about cooling the IGBT module and why it's important, why it's one of, in fact, the most important aspects about using an IGBT module is the cooling. But before I get into exactly how to cool the IGBT, I'm going to talk about the effects of cooling and not cooling an IGBT. The effects of when an IGBT is running at a high temperature and when the IGBT is running at a low temperature. So, hold on. Now, like I was saying, the temperature of the IGBT. Now we know that the gate resistor has a very important role in the IGBT. We know that a higher resistance gate resistor is going to make it switch slowly and a smaller one is going to make it switch very quickly. Now the interesting thing is that the temperature is very much similar. The effect may not be as profound, but it is there. With a higher temperature, the IGBT is actually going to switch slower. And with a lower temperature, it's going to switch much faster. But it actually goes beyond that. With the IGBT running and the temperature changing, as the temperature increases, it's actually going to take more energy to get the IGBT to switch at the same speed. And vice versa, when it's cooler, then it actually takes less energy from the gate driver to switch it off, even within the same value of the gate resistor. What else is interesting about the IGBT? Because the IGBT at heart still is a bipolar device, that means that the hotter it gets, the better it conducts to a point. I know that doesn't really make a lot of sense since most conductors, as they get cooler, they conduct better, but the IGBT is different in that way, and that can also lead to severe problems like thermal runaway. That is, when the concentration of the electrons gets so high that the IGBT actually can't contain it, and the cooling system may not be able to cool the IGBT fast enough, and it goes into thermal runaway, and the IGBT eventually then doesn't even want to shut off, and if it's in an inverter, then it will shoot through to the other side, it will short out and possibly explode. Now, there's more. Now the other interesting effect that cooling really has on the IGBT is actually its physical size. If we take a look at something like this, it has a relatively large physical size. This is 400 amps compared to one of, say, 100 amps. A 100 amp one is much smaller. Now obviously you're thinking, current goes up, the bigger it gets, but why do we need it to get bigger? The reason that we actually need it to get bigger is because of the dissipation of thermal energy. That means if we have something that's going to dissipate more heat, it's going to need to get bigger so the temperature won't increase. Now, before we go any further, we're going to have a very, very basic lesson in thermal energy. Okay, so thermal energy and heat. Most people, they think that heat is just the art of something being hot. But heat is actually thermal energy moving from one place to another. Now we know that in electricity, if we want electric current to flow, we need to have a difference in voltage. And if we want, say, water to flow, we need to have a difference in water pressure. For thermal energy to flow, we need to have a difference in temperature. The difference in temperature is what makes the thermal energy flow. Now, if we take a given amount of thermal energy and package it in a very large physical size, that means the temperature is going to be lower. And we can also put that into a smaller size, and the temperature will be higher. So just like with electricity, we can exchange current for voltage, and the thermal energy is similar. If we put it in a smaller package, we can get more pressure or more temperature. So, just to demonstrate, I have an old piece of insulation, and if we put it in front of the light bulb, which is 55 watts, not much happens. It is getting warmer, but it's not getting very much warmer because the thermal energy is very much spread out. But if we use the magnifying glass, we can concentrate the thermal energy, and we should be able to see something happen on the piece of insulation. It's just a little bit smoking. I don't think it will quite burn it, but if you can see that smoke, you probably get the idea. So, now that you know a little bit, very basics about thermal energy and heat, you can come to the conclusion that if we want an IGBT to stay cooler, we make it bigger because we're going to have more area and it's going to be easier to dissipate heat. And we know that an IGBT makes heat because it's not a perfect conductor, and we can even come pretty close in estimating just how much heat it will make. So all we have to do is make it bigger, right? Well, don't forget what these things have inside. They've got wires, and they have inductance, and the bigger we make it, the more inductance there's going to be. And it's always a fight over inductance. So, what do we do? Okay, just a few more things that I want to explain to you before we move on to the demonstration. Now, as I said, bigger IGBT usually means cooler IGBT. We can get more current out of that IGBT, and the temperature won't run away, but the bigger it is, the more inductance it has. The more inductance that it has, the worse that voltage spike is going to be, and the slower that we're actually going to have to switch it because of that voltage spike. That means while the gate driver is going to have to discharge a very large current, the switching frequency of the IGBT itself is going to have to be limited. When we talk about megawatt class modules, really big ones, they only switch those at very low frequencies because of that. Now, if you look around on YouTube, some places on the internet, you can listen to these trains running, the electric trains. You always hear that characteristic noise that they make. It's a very low frequency kind of whining noise, and that's due to the low switching frequency of the IGBTs. But what can we do to fix that? Well, if we make the IGBT smaller, it will have less inductance, obviously, and that means that we can drive it harder and we can drive it faster. But because of its small size, that means it's going to have difficulty eliminating or dissipating its thermal energy, because the temperature difference is going to have to be very high to get rid of the same amount of thermal energy. At the same time, if we make a bigger one, like I say, more inductance, and that means more gate drive power, because we don't want that heat and we're going to have to drive the gate really hard because of that. What happens with that is, because of that voltage spike, that means we're going to have to add on capacitors, more capacitors to deal with it. That drives up complexity and cost, and then we're going to have a gate driver that discharges a higher current. Guess what? Bad news. Because then that means now you're dealing with the inductance of the gate driver. Because as the current goes up in anything that switches, so does the voltage spike, because V equals L times di dt. So the greater the current is, the more the voltage spike is going to be, the greater magnitude the voltage spike is going to be. So then they have to get crazy. They have to start making the gate drivers smaller and smaller, and the circuit boards get closer to the IGBT with very short gate driver traces, just so we can supply enough current to turn the IGBT on and off quickly. And the bigger it gets, the worse the gate capacitor gets too, because that's going to grow, because we've got more chips in there and it's going to take more energy to turn those on and off quickly. So it's just a downhill battle with inductance and thermal energy. But there is a solution, and that is better cooling. So most people think with air cooling we can go a step further than that with liquid cooling, but remember this, just as I explained, the only way that heat is actually dissipated is a difference in temperature. And if we have a liquid cooling system, that means the IGBT still must be hotter than the liquid in the liquid cooling system. And that might not seem like that big of a deal, but the IGBT does have a thermal impedance. And that is because it has to be packaged on a insulating layer that insulates it electrically. So that means whatever happens, the IGBT must be higher than whatever medium that you're using to dissipate heat. Now, some people have said, let's just make the IGBT run hotter, and that will give us a greater difference. But those little bond wires in there, they start to crack because of the thermal stress of expanding and contracting. And then some people have said, let's just put spring contacts on it to keep that IGBT and those bond wires from moving too much, and the spring will compensate for the movement, and we can have them running at high temperatures, like something crazy like 200 Celsius. Now that does solve the problem of thermal impedance, but that's still very high, and as I explained before, the hotter it is, the more energy it's going to take to turn on, and the more likely it is to stay on once it's on. Even if we tell it to turn off, even if we take the gate charge out, it still wants to stay on. So, all that said, there are limits that the manufacturers recommend. They recommend only running an IGBT at half of its voltage and half of its rated current, and using the full capacity of the IGBT just in case for an overload situation. But is there a solution that we can use so that we can get... Nah, that camera cut me off. But as I was saying, is there a solution that we can use to get the full current and more out of the IGBT module while still making it smaller, having low inductance and low gate drive power and low noise? Is there a way to get all of those to happen at the same time? And there is. And I'll show you that in a minute. Slight correction. I meant to say it's an uphill battle between cooling and inductance. So, what is the solution then? What's the secret? How do we make the IGBT smaller, run cooler, have more current, less gate power? What is the trick? This is it, guys. Lower the temperature. How do we lower the temperature? How do we get the temperature of the heatsink that's making contact with the IGBT? How do we make that cooler? With one of these. A refrigeration system. Now, this one is a chiller, so it cools liquid. We're going to be running it through the heatsink of our IGBT test setup. I'm going to show you the IGBT running with a larger than recommended gate resistance value and a greater than recommended current value. But in a minute we will see that. I want to tell you, with a refrigeration system, I think it would actually be much preferred over a liquid cooling system, simply because if we can get the refrigerant evaporator to take place of that water block, then that means we will not have to worry about leaks. We will not have to worry about leaking water or coolant onto the power electronics. If there is a leak, it will only be gas. And we can get very, very, very low temperatures. A lot of studies out there say it. The lower the temperature is, even down to cryogenic temperatures, the faster the IGBT switches with less gate power. And that means we can make them smaller with less inductance. So, are you ready to see it? Alright guys, so this is our test setup. Have the same IGBT, have the same snubber capacitor. Now the larger capacitor has been replaced. I'm using a smaller capacitor with the laminated bus, and has a similar timer circuit, except it's a 555. It's in pulse width modulation right now. The gate driver, last time we used the highest one was 110 ohms, is about 103. We got the pump. We have the chiller. Water temperature right now, let me focus, 39.6 Fahrenheit, 4.1 Celsius. This is our load resistor. I'm using just the middle, that's 2.2 ohms. And power source will be the batteries. I'm going to give them a workout. Voltage 313 volts, and of course we have the scope. So, last time we saw with the 20 ohm gate resistor, we were jumping up to 2 times the input voltage, and that was just with that little spotlight. That was only 55 watts. But with that much voltage and that little resistance, we're looking at 130, 140 amps. But because we have the cooling system, we can put on a larger than recommended gate resistor. The IGBT will not be destroyed, and will make a very nice curve. So I'm going to start the output. We're going to take a look at that scope. It's going to be loud. Now if you look on that, flat. Even right down, it's flat. We do get small a little bit. Very nice, very clean. So, prove the point. It can be done. The maximum recommended gate resistor for this is 83 ohms. And it's not recommended to run it at that current because it's only rated for 75 amps and 600 volts, and that was right around, just around almost 140 amps with that kind of voltage. Now, that current may not have been coming out of the battery, but we were pulsing it, so we were getting it in a pulse. And we were at a very low pulse width actually, so that was even harder on the IGBT. So, guys, I hope you enjoyed it. I hope you learned something. I'm going to do another video regarding the gate driver because of a request. But for now, take care. Just for the heck of it, how much do you think the batteries can take? Oh, it's all they've got. Yeah, they won't do any more than 60 amps. Oh well. See you guys.